to find the values of the six trigonometric functions for pi over 3 or 60 degrees, well, all we have to do is refer to the order pair that we already have, for which we know a couple of values. And again, one thing to keep in mind is that the x component is the cosine function and the y component is the sine function. All right, so usually, again, when we're given an order pair on a circle, not necessarily a unit circle, but for now we're going to deal with unit circle, well, we have two freebies already. So we have the values of sine and cosine, where sine is the y value, that's root of 3 over 2, cosine, which is the x value, that's our 1/2. And we know from older identities, well, from older material, that tangent is the quotient between the y coordinate and the x coordinate. All right, that being said, we are going to find the ratio between the root of 3 over 2 over 2, root of 3 over 2, root of 3 over 2 divided by 1/2. Well, so we have a complex fraction here. And for this complex fraction, keep the fraction in the numerator, root of 3 over 2 times 2 over 1. That's how we divide fractions. So essentially multiply by the reciprocal of the fraction in the denominator. And we'll notice how these 2's go away, and our final answer is simply root of 3. So later on, when we start working on calculations involving trigonometric functions and their values, we will refer to these values from the unit circle. So at first, well, we might be using that unit circle whether from a separate sheet of paper or on a cheat sheet or something, or if you prefer the reference angle, the popular angles, that's fine. Either way you learn it should be fine, as long as you get the same results. And well, maybe for some time we will be looking back and forth between those cheat sheets, but after a while this just becomes second nature, and then we'll look at, oh, it's pi over 3, okay, a larger height, if it's sine, well, it's a larger value, other ways to obtain this function, to obtain these values. Well, we're done with sine, cosine, and tangent. How about the next function, which is cotangent? I'm going to write the cotangent function just below the tangent function, because we know that the cotangent function is the reciprocal of the tangent function. So all we have to do, you could do the x over y. Why not? X over y, I'm going to do that actually. And that's going to be 1/2 over root of 3 over 2. Complex fraction to begin with. And, well, again, dividing by a fraction is the same as multiplying by the reciprocal of the fraction in the denominator. That means then we can divide out the 2's. And this will be 1 over the square root of 3. But this may not be an okay answer. That's because, well, different homework systems such as, well, in our case, the ALEX system, or others like WebAssign or MyMATLAB from Pearson, depending on what you have used before, usually they're picky with this kind of answers, and they're not going to accept this. They want you to rationalize the denominator, and let's go ahead and do that. So that's multiply and divide by the square root of 3, essentially multiplied by 1, but in a special way that cancels out that radical in the denominator. All right. So that's root of 3 over 3, and, well, that's final answer. An answer with no radicals in the denominator. All right? So what do we have? Sine, cosine, tangent, cotangent, and Let's go about the reciprocal function for cosine, which happens to be secant theta. Well, if cosine equals 1 over x, because secant is the reciprocal, that has to be 1 over x. And in this case, this is 1 over 1/2. And dividing by a fraction is the same as multiplying by the reciprocal. That's actually 1 times 2, which is simply 2. This one was easy and short to compute. What about the next one, the last one actually, sine whose reciprocal is the cosecant function? Well, if sine is represented by the y component of the given order pair, well, since the cosecant function is actually its reciprocal, how about we just do 1 over y, that's the reciprocal. And well, that's going to be 1 over the square root of 3 over 2. And well, this one will require a bit more of work rather than the secant one, because check this out first. Number 1 is equals to 2 over the square root of 3. I mean, multiplying by the reciprocal and times 1. I don't think we still need to do the times 1. And how about multiply and divide by root of 3 to rationalize the denominator. So that's going to be 2 root of 3 over 3. So those are the values of the 6 trigonometric functions for the angle of 60 degrees or pi over 3. All right? Again, notice here we're giving the angle on both notations, in both forms. Number 1, this is radian measure, and this is degree measure. All right? Well, depending on the situation, you may be given one or the other, or both, or you may be asked to represent one way or another. But of course, we already know how to convert between one system and the other system. All right, what's next? Let's do the same thing. But now for the 30-degree angle, which is pi over 6. And again, this notation here is given in radian form, and this is in degree mode. All right, this is degree mode. All right, and well, we're given the order pair related to the angle of a 30-degree angle. And again, when we're given an order pair, there are already two functions given away. There's already two freebies, that is sine, which in this case is the y value, that is 1/2. And the other freebie, the other piece of information that it's pretty much given, it's the cosine function. Cosine theta equals x, which in this case is the square root of 3 over 2. So you will find out how, in this case, essentially the x's and the y's get interchanged. I mean, it's the same values, it's the same 1/2 from before, it's the same root of 3 over 2 from before, but this time they're interchanged. And that's because of the orientation of the angle right here, of the triangle that's projected by, I mean, it's a different color. It's projected by this point. So this point on the unit circle creates a projection of a right triangle, and that in this triangle in particular is the classical 60, 30, 90-degree triangle. So depending on the orientation, just reverse these two values from the given order pair. All right, that being said, how about we go about the remaining 4 trigonometric functions, that is the tangent function. The tangent function, that's the quotient between the y value and the x value. And simply, well, I mean, they're given here. Just get it from there. That's a 1/2 divided by the square root of 3 over 2. And same situation as we did before, as we did in the previous example. Dividing by a fraction is the same as multiplying by the reciprocal. We can go ahead and divide out the 2's. That's going to leave us with the following, that is 1 over the square root of 3. But again, the homework system may not accept this as a final answer, so we may need to rationalize the denominator. So, and well, we know how that works already. So just multiply and divide by root of 3, all right? And that's simply going to give us root of 3 over 3. Okay? Now that we have the tangent function, how about we go about the cotangent function? Cotangent, which in this case is the reciprocal of the tangent function. Notice how I'm writing the remaining 3 functions below the 3 basic functions, sine, cosine, and tangent. And that's so we can easily refer to their reciprocals and get those values from there. All right? So cotangent, which is the quotient between x and y, as opposed to tangent, which is the reciprocal y over x, and we'll just refer to the values that we have from the circle right here, and in this case the x is root of 3 over 2 divided by 1/2. Same story as before. Dividing by a fraction, that's the same as multiplying by the reciprocal. And we may go ahead and divide out the 2's, cancel the 2's, and that's going to give us the square root of 3. So again, you might notice the pattern, how we are getting exactly the same values as before. It's just in different locations. In some, everything containing the x became a y and vice versa. So that's why these values sort of look familiar. So what do we have? Okay, so we have sine, we have cosine, we just found tangent and cotangent. Let's refer to cosine to find its reciprocal, which in this case is secant, which is 1 over x, that is 1 over root of 3 over 2, and again, dividing by a fraction, that's actually the same as multiplying by the reciprocal, which is 1 over, not 1, I'm not going to write it, 1, 2 over root of 3. And make sure to rationalize the denominator. That's multiplying across in the numerator, that's 2 root of 3, and in the denominator, radical times itself, just come up with the quantity inside of the radical. I'll explain that in a minute, how it just works to multiply and divide by the radical, in case you need to review that. So let's just finish this with the last function, cosecant. That's well, if sine is y, it's a reciprocal, which is cosecant, that's got to be 1 over y. And in this case, that's 1 over 1/2, which is simply 2. So those are the 6 values of the trigonometric function for the 30-degree angle, or pi over 6. Now, the quantities in the denominator that I've been computing in order to rationalize them, well, different color. Yep, this one. Well, the way this works, that's because multiplying numerator and denominator by the radical, so that's going to give us the following, root of 3 times itself. So one way to go about this is the following. Number 1, convert these radical numbers as 3 to the 1/2 times 3 to the 1/2. And then if we, since in this case we have the same base, we are going to add the exponents because we're multiplying the bases. If we were dividing the bases, we would be subtracting. And in this case, well, that's going to be 3 to the 1/2 plus 1/2, which is 3 to the 1 to the first power, which is 3. And notice our final result does not contain anymore a radical. So that's the process known as rationalizing a denominator, to have an expression that contains a radical in the denominator with no radicals at all in the denominator. And well, and it works just as straightforward as multiplying numerator and denominator by the same radical. Another point of view, root of 3 times itself, this is the same as, and maybe it's the shorter way, to interpret it, that's the same as saying root of 3 quantity squared. And from here, we can keep in mind that the square and the radical are opposite operations, just the same way multiplication and division, addition and subtraction, exponential and logarithm, logarithm and exponential. Well, squaring and taking the square root, those are opposite operations, and that equals to 3. And well, rationalizing denominators containing square roots, they are actually the easiest case because it just works. It just works by multiplying numerator and denominator by the same radical. However, and I'm going to take a little detour here. I think it's important because this same process doesn't work for other kinds of radicals like cube roots, fourth roots, etc. Let me make something up over here. Let me see if I have space. Okay, let me erase this part instead. We don't need that anymore. What if I have something like 1 over the cube root of 2, for example? In this case, well, if we go with the same pattern as before, oh yes, well, it should work to do the following. Why not? So yes, final answer, cube root of 2 over 2. Unfortunately, this is wrong, and the reason to that is because, well, the implied operation here, when we do this, the one in the denominator, check this out. Let me do it in a different color. So I'm going to take this in a different color and a different location. That's the cube root of 2 times itself. All right, that's the same as saying the following, 2 to the 1/3 times 2 to the 1/3. Do the exponents add up to 1? So what do I need to add this 1/3 with in order to obtain a 1 as a result? That is 1/3 plus what number? 2/3, all right? 2/3. That's going to give me the 1. Then I will need the following. Add a power 2, add a power 2. All right? And well, this will become the following. So that's the cube root. Well, simplify to 4 because 4 is not a perfect cube, so we are fine with it. And then that's just going to be 2. And that's the correct way to rationalize a denominator for which the radical is an index other than 2. And of course, I mean, we can come up with something crazier, but the magic thing here is to find enough powers to get a 1 overall, so that radical simply disappears. And for example, let me just do one more example to show you this, and then I'm going to go back to trig. So what's it? Let me do one with even with a variable. So that's 1 over the 5th root of 2x squared, for example. All right. Again, following the original pattern, I don't think it's going to work to simply go, oh, the 5th root of 2x squared and the 5th root of 2x squared. No, because that's actually 2 to the 1/5, x to the 2/5. All right? And multiplying that by itself, 1/5 plus another 5th is not going to be, unfortunately, 1. And here, x squared, that's actually 2/5 plus another 2/5. That's only 4/5. We are 1/5 short to get the integers. So in this case, check this out. The way we go about this, let me write the bases. And the bases are 2 and x. So now, the fact that I have a 2 here, that implies that I have a 2 to the 1st power. That means I have only 1 2 out of 5. I need additional 4 2's to have a total of 5, which will become 5/5. Do the same in the numerator. For the x's, I have 2 out of 5. I need 3 more to have 5/5, which is equal to 1. And so, well, 2 to the 4th power, which is 16, but 16 is not a perfect fifth, so we can just go ahead and write it down. 16x cubed over, that's 2x. All right? I know this is a little off topic, but we may run into situations in later topics, or you may run into these situations in, I don't know, maybe in future courses like calculus or other engineering courses in which you may need to work and manipulate radical expressions, radical functions. So it's important to keep in mind. So now coming back to trigonometry, so that's why it works to just multiply and divide by the same radical, because here what do we have? We have a 1/2 plus 1/2, that's one integer, and that cancels that radical expression. All right, the table below actually summarizes all we have done since the last class and today. You know, all the values of the trigonometric functions for the 45-degree angle, or pi over 4, and the values of the trigonometric functions for the 30-degree angle and the 60-degree angle. So today we cover these two, this first row and the third row. Of course, those are not values that you have to memorize like today, but again, these will come in applications in which, again, you will find ways to learn that unit circle. There's actually a lot of tricks that you can find online, and number one, well, it's knowing the unit circle, knowing the basic triangles, and well, now we're going to generalize all this about the unit circle, because right now, well, up to this point, we have worked with the values of the trigonometric functions for the 45-degree angle, 30-degree angle, and 60-degree angle. However, we only work on those when the location is the first quadrant. Now, we can generalize to have that same angle, pi over 6, and its multiples, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And notice the pattern. Notice the values that we have for x and y. They are exactly the same. Root of 3 over 2 comma 1/2. The only thing that changes in this case is the sign of one of the values, and that's going to depend on which quadrant are we. For example, for the values of the trigonometric functions for 5 pi over 6, well, notice how this we can use our y-axis as a mirror to reflect this point about the y-axis. And when we reflect functions about the y-axis, well, that's going to take us back to the beginning of the semester. Remember when we did transformations of functions? Well, when we transform functions, what we're really doing is transform points one at a time. But I mean, when we talk about a function, we just carry every single point in one compact expression, you know? But well, in this case, check how this point in the second quadrant is a mirror of the original point in the first quadrant, but because in the second quadrant we have x negative and y positive, check the signs, right? What about the point on the third quadrant? Well, that point is a reflection of the point in the second quadrant, but reflected about the x-axis. So the x value will remain the same. However, the y value will change to positive. And the last value right here, the last point rather, the point on the fourth quadrant, well, there's actually a couple of ways to describe it. Number one, this point to be a reflection of the point in the third quadrant about the y-axis, that is, change the sign of the x, or this point to be a reflection of the original point in the first quadrant about the x-axis, and all we do is simply change the y value to a negative sign. Either way, we should get the same thing. Compare that to multiples of the 60-degree angle, and again, check this pattern again. Check this out. 1/2 root of 3 over 2, root of 3 over 2, and 1/2. We have these coordinates reversed when we are dealing with a 60 and 30-degree angle, or pi over 3, pi over 6, respectively, angles in radians rather. And well, the idea of getting the same signs on the other quadrants, it's the same way to generate it. Just keep in mind the signs of the values in the four different quadrants. First quadrant, all positive. Second quadrant, x is negative, y is positive. Third quadrant, both values are negative. We go negative. we go backwards, and then we go down to negative. And fourth quadrant, it's positive, then negative. See the pattern. Check the sign. So the sign, the pattern sign gets repeated. Check negative, 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 all negatives, all negatives. Only y negative, only y negative. That doesn't change. All right. And well, so the last one, this it's going to be the 45-degree angle. And for all of them, I mean, I don't think there anything can go wrong because both x and y are root of 2 over 2. So I don't think there. I mean, what could go wrong about it? The only thing that you might need to be aware of is depending on the location that you are at, just change the sign of either the x or the y depending on where we are. That's all it is. All right? Well, these three separate circles were to describe the pi over 4 and its multiples, the pi over 6 and its multiples, and the pi over 3 and its multiples. How about we look at the whole thing this time? And that's on the next page. And that's our lovely unit circle having pretty much everything. And that's a sheet that I would advise you to print every time you're working on a homework. Use it like as your, or other classes like chemistry or something that you do flashcards to memorize um, this what like nomenclature, ions, cations, and anions. What else? Formulas and facts. Well, so we can use this unit circle, print it, make it big, make it a poster, put it next to your mirror, on your back door, whatever, so you can see it all the time and look at it all the time. Because I mean, this is what you will be using for the rest of your engineering career. I mean, this is like the alphabet pretty much, right? Like the numbers from 1 to 10 for the rest of your life as scientists, engineers, and the like. Question?
Will this be on the, will the unit circle be on the exam?
I don't think so. I don't think so. So yeah, that's why I was talking about make it a poster, put it on your door. Yes.
What's the latest thing that we have covered that's like on the test?
Good question. I'm thinking last topic, 6.1. But you know what? Let me verify that information. And well, actually, I have to send an email with Google Docs. So you guys, for those of you who need to sign up for the makeup exam, and I will include that information as well. So I just need to check in with the course coordinator, right? So yes, this is the one that you want to memorize. I would say tattoo it, but if you go to an exam with a tattoo of the unit circle, most likely they'll kick you out for cheating. So don't do it. All right, don't do it. All right. Ha. Okay, find the exact value of the following. Well, find the value of cosine of 5 pi over 4. All we have to do, go to 5 pi over 4 and identify the cosine function, which, by the way, that's just the x-coordinate. Easy. Negative root of 2 over 2. We're done. Yes, it's that easy. That's all we do. Now that we have everything together in the unit, so of course what we did is do one angle at a time, and in the end, well, we got this. Well, whenever it's sine or cosine, it's the easiest because all you have to do is look at the x or the y. X for cosine, y for sine. Let's look at sine of 135 degrees. Well, one of the things I like about this unit circle, which by the way, I got it from a different book. This unit circle, it's not from our current book. This is like the most complete unit circle I have ever seen because it includes all the order pairs. It includes the angles on both formats, the degree mode and the radian mode. All right? Now, let's see. Okay, sine of 135 degrees. Look for 135 degrees and know that sine, it's only the y value. Right? That's it. Root of 2 over 2. That's it. All right, here is where things get a little tricky. What's next? Sine of negative pi over 4. Well, when we're dealing with negative angles, well, again, positive angles, I think we already talked about the orientation of the angles with respect to unit circles. So, I mean, we don't need to draw any arrows to show the orientation. I think we can see it from looking at the angles going in increasing order by going counterclockwise. However, every time we are dealing with a negative angle, that means we will have to go about clockwise on the other hand. Later in this section, we're going to look at the even and odd properties of trigonometric functions, and that has to do with how we evaluate a function at a negative, and in some cases, well, the function might be even or odd, and well, we will do something about that negative sign. But for now, we don't know what that is. Even if you have already seen it, well, let's pretend we don't know. Okay? So we're just going to go, okay, negative pi over 4. So pi over 4 is the same as 45 degrees. Negative 45 degrees would be this dude right here. And well, they're asking us for sine. That has to be the y value. Sounds good? Negative root of 2 over 2. Cosine of 8 pi over 3. Oh my god, that's well, I mean, check this out. The multiples of pi over 3, notice how they go. Okay, pi over 3, let me go back to pi over 3. So we go pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Well, I'm already going more than one cycle in this case, all right? That'll be 6 pi over 3, which is equivalent to 2 pi. That'll be 7 pi over 3. That'll be then 8 pi over 3. So 8 pi over 3 is really the same as saying 2 pi over 3. Remember how we talked about these trigonometric functions to be periodic functions, to be cyclic functions, because even if you go around the circle multiple times and multiple times, eventually you fall back in the same points for different rotations, and they're multiple. So this is an example. So this is you don't have to do this. However, it would help to rewrite cosine of 8 pi over 3 as cosine of 2 pi over 3. Because, well, ultimately, these are coterminal angles. You might remember we talked about coterminal angles, how we go back to an angle that lies in between 0 and 2 pi, or 0 and 360 degrees. But in this case, we add a multiple of 2 pi or multiple of 360 degrees. And we fall back into the same point once again because of the periodicity of these kinds of functions. Well, cosine of 2 pi over 3. What's that? Let's go to 2 pi over 3. Oh, that's just negative 1/2. All right? Tangent of 315. Oh, okay. Now, the unit circle contains points, a bunch of points. So there's how many? Let's count them. Why not? 1, 2, 3, 4, 8, 16 points, 16 main points based on multiples of 90 degrees. Those are the quadrantal angles. Remember how we talk about quadrantal angles? Those are the angles that lie in between two quadrants, like the 90-degree angle, the 180-degree angle, the 270, and 0 or 2 pi. All right? And then the multiples of 30 degree, 45, and 60 degree. Those are all of our angles here. All right? But those points right here, again, they describe a cosine and a sine. Now, they're asking us to find a tangent function. And let's recall that the tangent function ultimately it's the quotient between the between the y and the x. So tangent, which is y over x. So let's go about 315, and well, again, it's right here, 315 or 7 pi over 4. And in this case, we're not going to choose between one or the other because we're not being asked to find a sine or a cosine. In fact, they're asking us to find the quotient of the two. So that's going to be negative root of 2 over 2 divided by root of 2 over 2, which is in this case negative 1. And cosine up to 10. Let's go about cosine up to 10. Identify the 210 in degrees in radians since we want cosine. And that's negative root of 3 over 2. As easy as looking at x and y, except that if we were evaluating a tangent, well, we need then to, to do a quotient. Well, something I didn't do. Let me make something up here. How about secant of 5 pi over 3? Right? Secant of 5 pi over 3. Well, again, those points on the unit circle only give us sines and cosines. All right? So, well, we know we can relate the secant function to the cosine functions because we know that the secant function is the reciprocal of the cosine function. So then we can evaluate the cosine of 5 pi over 3, which happens to be here, 5 pi over 3. Cosine equals to 1/2, and that's, that's 1 over 1/2, and dividing by 1/2 is the same as getting a 2. Right? And I mean, if you look at all these results we obtained, those should look familiar from what we did before when we broke down number one, the 45-degree angle, and then like we did last time about breaking up the 30, 60 degree. But today we got those values for their trigonometric functions. So either one way or another, so they should be familiar. So we'll no longer go with every single separate triangle or part of the circle. Now we have everything all together in the unit circle. All right, and again, that's something you need to memorize. All right, as far as I know. If anything changed, I will let you know. All right, let's see what's next. Determine the domain and the range of the trigonometric functions. All right, so the ones that we don't really need to worry about are sine and cosine because those are pretty cool functions whose domain are all real numbers. That is, we don't have any asymptotes, we don't have any holes or any jump discontinuities. They are very well behaved functions, pretty continuous functions. And I mean, let's look at their graphs. Even though the graphs are more like the objective of the next section, I mean, I think it's safe to do something about it. So let me get rid of this. So that's a sine. I know we're working with thetas, but the dummy variable by default for the graphing calculator is x. All right, graph. Hey, what happened here? Mode. Oh, it's in degree mode. There you go. So this function, check this out. Notice how it doesn't have any jump discontinuities, any holes, any asymptotes. So that's why we can tell by looking at the graph that the domain is indeed all real numbers. What about the range though? The range just go between -1 and 1. So, and we can see that on the graph. I mean, check the maximum value of the sine function by looking at the graph. Notice how it goes up all the way up to a maximum value of 1 and all the way down to a minimum value of -1. So that's how we can see that indeed the range of the function is -1 to 1. the cosine function, and actually I'm gonna graph it in the same grid. It looks the same shape, except that it's just shifted 90 degrees or pi over 2 units. We're gonna look at those details in more detail, more in depth later when we look at shifting of functions, phase shift, how cosine and sine are really shiftings of one another. And check the domain. I mean, check the graph in red. No asymptotes, no holes, no jump discontinuities or gaps. Minimum and maximum are 1 and -1 respectively, which checked with the data we have over here in our definition box. The ones that are a little funkier, however, are going to be the remaining ones: tangent, cotangent, secant, and cosecant. All right. Let me draw the graph of the tangent function. That's not one that it's very easy to draw by hand. So let me go and clear. Oh, hold on. All right, that's tangent x and graph. All right. See how the okay? You know what? Let me add the sign again, just so you can see the periodic properties, the periodic shape of this function. So see how the sine function completes one cycle doing this, and then starts another cycle, and many cycles. All those cycles repeated are the equivalent of going around the unit circle in the set of values that we had on the previous page. All right? So however, in this case, the period for a sine function, so that function completes one cycle or one turn every 2 pi units or 360 degrees, as opposed to the tangent function, which doesn't do it at every 2 pi unit, but it actually does it every pi unit. However,